In this video, we're going to continue with examples on the dot product of two vectors. So to start off with, I'm going to give you two vectors v and u, and I'm going to give you the following elements. And just to keep it simple, I'm going to confine this problem to two dimensions. So we just have an x and y axis. So we already defined how the dot product of two vectors a, b is just the sum of the components. So ak, bk from k equals to 1 to n, where n is just the number of elements they have for the number of dimensions. So in this case we would have, because we have two dimensions, a1 times b1 plus a2 times b2. And we also define the vector as the projection of one vector onto another and then multiply by the total length of that new vector. So we can also define the dot product of two vectors as the magnitude of a times the magnitude of v times cosine theta. So theta is just going to be the angle between the two vectors. And in this case, we can actually use either of these to find the answer. Now, which of these two formulas do you think we should use? Well, we're not really given an angle. We could use some geometry to find the angle, but that will require some extra work. So how about we just find the dot product using this formula? We have the elements, so we can do it in a very straightforward manner. Now, you will find, and this is a very important thing, that it does not matter in which order you take the dot product. So in this case, if you have v dot product with u, it is essentially the same as having u dot product of v. And the reason for that is that you will notice that if you change this operation around, then all you're essentially doing is you're switching the order of multiplication here, so that becomes b1 times a1 plus b2 times a2. And we know that multiplication is commutative, so you're going to get the same result from these two operations. You're just adding them together. So this is the same as that. So it does not matter in which order we do it. Now the next thing we're going to do is obviously take the components. So I say 1 times 3, so that's going to be 3, plus 1 times 3, so that's 3 again, and this is going to be 6. So basically we just obtained a length. So this is what the scalar product, what the dot product of two vectors, sometimes it is called the scalar product of two vectors, is just a scalar value, and it represents a length, and we'll see what length it actually represents now. So we know that if you take two vectors, then if you project one of them, so if this is a right angle triangle here, you project one of them onto the other, so you can imagine this is the shadow cast by this vector onto this one, and this one has some magnitude. So let's say this is a and this is b. This has magnitude a times cosine of theta, where this angle here is theta, and then you multiply this by the total length of the new vector b, then this is just the dot product of the two vectors. So in general terms, when you multiply two vectors by using the dot product, what you're getting is you're getting a new vector, and that new vector is going to have a much larger length. So if I were to draw b for comparison here, b would actually go somewhere around here, a is somewhere around here, and then the projection of a onto b would come up to here somewhere. So this would be a cosine theta. Then this total length here would be b. So basically b is going to go all the way here, from here to here. And then the length of this new vector, which results from the dot product, is going to be a times the magnitude of b times cosine of theta, which is just the dot product of the two. So you're not getting really a vector, but rather you're getting the length of a new vector, and the length of that new vector is related to the length of this projection times this length. So essentially the dot product of two vectors is a magnification, or a it can be a diminishing process, because if you projected B onto A, for example, if you were to project B onto A, you need to make sure that it is at right angles with the line of where A goes. So obviously, because this is longer than that, then when you multiply it, you would still get the same result, but it would be a different way of looking at it, I would say. But in general, the dot product is just a magnification process. You're taking two vectors, you're creating a new vector, and you're finding the length of that new vector based on those two operations. So this is a really, really important concept. Now, just for the sake of argument, let's say we do another example. Let's do a three-dimensional example. And we're going to make it a little bit more interesting this time. So let's say we have a set of three axes here, x, y, and z. Now we're going to have some vector going this way, let's call it A, some other vector going that way called B. So I'm going to give you the coordinates now. Let's say this is 1, 0, 3, and then B is going to be 0, 4, 4. So the idea is we want to find the angle between those two vectors. So we want to find the angle of those two vectors. How do we do that? Well, there's a very simple way of doing it. Remember that we define A dot product with B as the magnitude of A and B cosine of theta. So all we would really need to do here is we would need to rearrange this. So we would have cosine of theta equals to the dot product over the magnitude of the two vectors multiplied together. And we know that this can be represented as the sum of the components. So we have AK, BK over the magnitude of A, magnitude of B. And then all we need to do to find the angle between those is just take the inverse of cosine, and then we get the following. So that's it. That's how you find the angle. So let's proceed and do that. So the first thing is we're going to find the dot product of A and B using this formula here. So the sum of the elements. So we're going to have 1 times 0, that's 0. 0 times 4, that's 0 again. And then we have 3 times 4, that's 12. So this is 12. So what this represents is the length of a vector that will result from multiplying the projection of A onto B or B onto A by the length of that vector it is projected onto. And now we're going to calculate the magnitudes individually. So the magnitude of A in this case is going to be what? So we're going to have square root of the following values, 1, 0, and 3. So 1 squared plus 0 squared plus 3 squared. And this is going to be 1 plus 9, so that's 10. And then the magnitude of B is going to be the following. So we have 0, 4, and 4. So 0 squared plus 4 squared plus 4 squared, which is equals to 32. And this would be equal to 16 times 2. And then if we take the square root of 16, that becomes 4 square root of 2. So that's fairly straightforward. We just find the two magnitudes. And all we need to do now is just calculate the angle by using this. So we're going to have angle between these two is going to be the inverse cosine. So we're going to have, this is just 12. And then we have square root of 10 times 4 square root of 2. And we should get the following. We get the angle 47.87 degrees. So I have just rounded up to 2 decimal places. So this is the angle between the two vectors as seen from a plane in which the two vectors are coplanar. So if we were to draw a plane like this, then this would be the angle along that plane. So this is just the general angle, or the smallest angle between the two vectors. And that's it. That's how you apply the vector dot product to find the angle between two vectors. And this is also very useful in mechanics, as we will see in some later examples. But for now, I just want to make sure that you understand the main concept behind this. So the vector dot product, we know that for any orthogonal basis, so a set of basis vectors that are perpendicular to each other, the vector dot product is just the sum of the elements, so the corresponding elements. And then it is also equal to the magnitude of the two vectors times cosine of theta, where theta is the angle between the two. And in the next video, we're going to go into a physical application of this, and we're going to discuss how to find the work done on a particle.